So good morning, everybody. My name is Jason Ingham, and I am chairing our session this morning. I am here at the University of Auckland with my co-presenter, Yuni Azhari. So this is our regular QuakeCoRE seminar series held every third Friday of the month. Next slide. So our presentation today is titled Testing and Modeling the Response of Unreinforced Masonry Buildings and Earthquakes. What we're going to try to do today is demonstrate to everyone what we've been quietly doing, basically following the Canterbury earthquakes and the Kaikoura earthquakes around the integration of experimentation and modeling. Before we move off this slide, I wanted to mention a couple of things. The first one is if you have a look at the image on the left, you're seeing an experiment that was undertaken in Pavia in Italy. And over the top of that, in the blue, is Yuni's numerical simulation. So you can see, as an example, about how well the correlation's working. And again, before we move off the slide, I really just want to acknowledge that throughout this presentation, we're going to be referring to a lot of work that's been done by Dimitro and Marta and Hussein and Paco. And I noted that Paco signed in today. So there's a lot of excellent work that's come before by students from the past. Next slide. Where does this all slot into QuakeCoRE? Well, in Generation 1 at QuakeCoRE, it was part of Flagship 3. Mostly the work we've been doing falls within DT2 whole of building seismic performance. But I also wanted to note that in conjunction with Tim Sullivan from the University of Canterbury, I've recently begun co-leading IP2 on thriving residential communities. So a bit of a scene setter. I'm sure everyone remembers the images in the top row. I think that along with the pancaking of collapsed concrete buildings, the damage to unreinforced masonry buildings in Christchurch was a very vivid memory that we all have. The wider public were very aware of the damage that old brick buildings can form. And then it sort of transpired that the Kaikoura earthquakes came along and there was remarkably little damage to unreinforced masonry buildings. This was because of the fact that unreinforced masonry buildings are very stiff. They get excited a very short period range on the spectra, and Kaikoura earthquake had a different sort of signature to the shaking. And so the old brick buildings didn't take as much damage. Nevertheless, despite the fact it's all been a bit quiet in the world of unreinforced masonry, we have continued to be quite active behind the scenes. What we have been doing is a variety of different sort of work. Here, what you're seeing is that when opportunities present themselves, we're able to extract samples from real buildings and bring them back to the laboratory and test them in the laboratory. This was work that was undertaken by Dimitro in his PhD thesis. Next slide. We've also then, where we can, have done field testing, which I guess is a primary opportunity for testing how real buildings perform. What you're seeing in the middle then is simulated response when we have constructed walls in the laboratory. And again, that was work that Dimitro led. And on the right then is the numerical simulation, and that's a simulation by Paco. And really, this is the first time we just want to emphasize or explain that we've been using a numerical modeling technique called discrete element modeling. It's very numerically intensive. Most of the time we're modeling each and every brick, but I really like to use this strategy, first of all, because you can completely confirm the mechanism that forms, and it's just the reality of the modeling strategy. What we've been doing is, where possible, taking advantage of testing undertaken in Europe at very large scale, and a number of these studies end up being blind prediction studies where the experiments are done and they only provide you with a very small amount of information. And from that, you have to attempt to match up your prediction against the actual results. On the left is a study that Hussein participated in, and in white is Hussein's crack pattern, and you can't actually see the real crack pattern, which is in red, because they exactly overmatch. So Hussein did an excellent job there of forecasting the mechanism of collapse. On the right is a study that has Paco participated in, 2 adjacent buildings that will be in contact. And Paco did extremely well in predicting the mechanism of collapse and the displacements that would occur. But in both of these studies, what's particularly fascinating, if you look at the text in red, is that many of the world's sort of leading academics that are hopefully developing sort of expert techniques are quite often out by quite large variations. So the complexity of these behaviors is such that the results tend to be a bit all over the place, which is kind of good because even if you do poorly, you're not the only one that's done rather bad, but it's also an excellent way of being able to develop your modeling skills. Next slide. What we've also been doing, and this is very much live this week between Yuni and Paco and myself, is all the way from the field observations, as you can see top left, and then only in the last couple of weeks, Paco's had one of his final papers from his thesis be accepted, which was all about mapping the progression of damage through to collapse. And right now, bottom right, we are working as hard as we can go to translate that research into practice in the national methodology for how to assess unreinforced masonry buildings. As you can see from the date there, it says June 2026. We quite literally are down to the last week or two of an exercise that we've been working on for about 2 years to get this information into the latest methodology. Next. Over to you, Yuni.
Okay, thank you, Jason. So as with the former students that comes before me and also encouraged by Jason and aligning with the intention to improve the seismic guidelines, I took on the challenge to also participate in the blind prediction study of the unreinforced masonry gables. So the experimental campaign for the blind prediction was conducted in conjunction with the World Conference of Earthquake Engineering back in 2024. The setup of this gable is pretty unique, where there is what we call a partial restraint imposed by the purlins here. On the left image, it describes the experimental setup where the unreinforced masonry gable placed on top of a shake table, and also with the purlins connected to a back frame and the back frame connected to the top and bottom table to induce compatible motions between each purlins. And the input motion that was given was accelerations of the top, bottom, and bottom table, and also on the ridge beam and each of purlins elevation. And from this experimental setup, I translate them to a numerical modeling. So the modeling approach that I opted for was the simplified micro modeling. As Jason explained before, it's a very exhaustive numerical modeling because it is both computerly hard and then also time consuming. So here I combine the brick and mortar into one unit, and between those units I applied the cohesion contact surface, which dictates the stickiness of the mortar in between the bricks, and that will be dictated also by the cohesive properties in the form of traction separation relationship, both in the what we call normal directions and also the shear directions. And with this modeling approach, I built the gable model for the blind predictions, where it's a initially pretty simple setup, only the gable model and the purlins and also the bottom table. And the way I impose the boundary conditions is by applying accelerations on the ridge beam at the top, at the purlins, and also at the bottom platform. And the result of my predictions was quite good in terms of the crack pattern. I predicted the crack pattern almost accurately, both for the case of rigid roof scenario and also the flexible roof scenario. But in terms of the peak-based acceleration, as with the other submission as well, I got an underestimation of the peak-based accelerations. And here I also want to highlight the same thing in the case of my blind predictions. The coefficient of variance for both cases is pretty large, which means that all the teams across the world, we all have a hard time predicting with limited data input. And after the experimental campaign is concluded, they gave us a more comprehensive data in which I can refine my model in the post-diction stage. So in the post-diction stage, I was able to refine the boundary conditions, the interactions, and also the input of the earthquakes. So here on the left image, I switch from the acceleration input to displacement input on the top and bottom. And because I have now applied a back frame behind the purlins to more accurately replicate the test setup, I am able to guarantee what we call a compatibility between each purlins and also the bottom table. And based on the results from the sensors and the tests, I am also able to refine the cohesive interface properties in between the units or the bricks, and also the interaction between the purlins and the brick units in the shape of friction interface that has not been clearly defined in the previous prediction model. And from this refined model, I was able to have a satisfactory result. In this case, for the stiff roof scenario. I'll just wait for the video to load. So we can see from both video on the right side, both comply in agreement really well. And on the left is just a snapshot of the collapse mechanism of the gable in the stiff roof scenario. For another cases, which is a flexible roof, although the main crack pattern still occurs, which is the horizontal line in between the purlins, there's a slight off in terms of the diagonal cracks of the gable. And for the gable responses itself, for both scenario, peak-based acceleration and top displacement were clearly matched satisfactorily between the numerical in red and also the experimental result in black. As for the control point displacement, there is a slightly off result, especially after the sequence in which the collapse mechanism starts to happen. For the stiff roof scenario on the top right, the collapse mechanism starts to happen after test sequence number 10. And for the flexible roof scenario, the collapse mechanism starts to happen after test sequence number 5. So lesson learned from that blind predictions basically highlights that we need to do experimental campaign in conjunction with the numerical modeling because of the uncertainties when it comes to detailed micro model. So here I'm tackling on another topic that is not yet well addressed in the C8 seismic assessment guidelines, which is pounding between adjacent unreinforced masonry buildings. So pounding between buildings will occur when two different dynamic properties, two different buildings with two different dynamic properties have inadequate gap. And then when earthquake occurs, they start to pound to each other. So based on the same flow with the test between testing and modeling calibration, here is the main step of the research that I'm tackling on currently. So what I'm doing is the preliminary modeling, and then from the preliminary modeling, we'll design the lab testing. So the reason of the preliminary modeling before the lab testing is because of the limited resources that we have. So in order for the lab testing to be cost effective, so biggest bang for buck, we do the preliminary modeling. And then after that testing, we will do the calibration with the model in order to have a validated post-test model to be able to extrapolate that into several cases in the future. As for the preliminary modeling, I started from modeling a 1/4 scale building of an experiment performed before by Marta. Marta is also Jason's former student. So here I model the 1/4 scale building also with the same method as the simplified micro model. And I managed to obtain a satisfactory result in terms of crack patterns matching, and also a good agreement in terms of peak table acceleration at the top graph, and then the displacement or the displacement and height relationship on the bottom figure. And from that preliminary modeling, I was able to extract the facade of the building and develop that into a parametric study of in-plan facades in pounding. So here, basically, I studied the variation in the height or number of story, variation in the opening size, and also variations in the gap between the buildings. The top row shows the amplification response of the buildings when pounding occurs compared to when the buildings stand alone without any pounding with the neighboring building. So the largest amplifications was 1.5 for the displacement of the 1-story building and 2-story building on the top right corner, and then the second to right is a whopping 1.9 between 2-story buildings. And here I also experiment with the opening in order to see the effect of the opening that is in correlation with the stiffness of the building as well, and also the gap. So the variation in gap here, I want to highlight that when the separation between two buildings is adequate, we can see that the pounding force on the bottom row decrease incrementally. So for the 2-story building, the pounding force starts to decrease when the separation gaps go up beyond 5 millimeter, and then for the 1-story and 2-story building, the pounding force decrease incrementally when the separation gap go beyond 2 millimeter. So based on the findings from this parametric study, I was able to design my building test specimen, which will also be in the 1/4 scale in order to fit the shake table that we currently have in the University of Auckland. And this 1/4 scale building will be built from a half scale clay brick to represent a double leaf wall. And the mortar that we're going to use will be considered as a weak mortar because we want the strong break weak mortar behavior where the crack pattern will mostly be predetermined based on the mortar layer. Yeah, and before doing the shake table testing, I'm currently doing the material characterization. So this material characterization will cover a bunch of testing to obtain compressive strength, flexural tensile strength, flexural bond between masonry, and also the shear strength of masonry bed joint. So all these parameters from physical properties of the brick and mortar will be translated into numerical properties of the model. So from that numerical properties of the model, we'll be able to predict again the result of the testing. And then after the testing, I will be able to calibrate and refine my model. So in summary, this is the flow of the projects that I do. So preliminary modeling and then lab testing and then post-test modeling. And then from this refined post-test model, we will extrapolate that into several cases in order to find a correlation and establish a procedure for quantifying pounding between two adjacent unreinforced masonry buildings that is more suitable for industry practice and hopefully be adopted to the future seismic assessment guidelines for unreinforced masonry buildings. So that's all about my project. I give it back to Jason.
Okay, so thanks everybody. We've got a number of takeaway messages that we just wanted to emphasize, but also I wanted to say that if after this webinar this morning you've got any further questions, do please feel free to reach out to us. The first message is that really, despite the fact over the last decade, I think the focus quite correctly has been on multi-story concrete buildings and other types of structures. You should be aware that it is expected that if we have future large earthquakes in New Zealand, we still have many unreinforced masonry buildings around the country. And if they are subjected to strong shaking, we can continue to expect the sort of damage we've seen in the past. In terms of a campaign, as Yuni was talking, I was thinking, gee, it's now more than 20 years since I began this work. So there's really clicking over with many students over a long period of time. But we wanted to sort of show to you today how we've attempted to combine our field testing and our field observations with our laboratory testing, how we then use our numerical modeling strategies to tie all that together, and then the work of Paco in particular and how we've managed to translate that into our national methodology. Another thing, if you are given the opportunity in any of the work you do to participate in international tests of any sort, I've certainly found that to be a wonderful way to stay connected to researchers around the world, but also to take advantage of the fact that these experiments are very expensive and very complex and very time-consuming. And so now, wherever possible, I attempt to get involved in them. So it's a very useful exercise, in my opinion, and something that I'd encourage others to do. As we discussed before, the end goal with all of this is to try to get our research into practice. That's something that I know continues to be very important to QuakeCoRE, and I think our work's been particularly successful in that regard. And as we sort of presented to you today, there's two topics within inside our national methodology that we're still putting a lot of attention into. One being that the response of complex geometries for outer plane behavior, gables in particular, but others with 3 and 4-sided boundary conditions, needs a lot of attention. And then right now, there is nowhere in the world where there is a national methodology to establish the pounding forces that are generated between adjacent unreinforced masonry buildings. And so that's where our focus, or Uni's focus, is currently directed. So thank you very much.